Welcome to Ask and Learn.
All right, so here we're interested in determining how many ways a 2 by n checkerboard can be tiled using 1 by 2 or 2 by 2 pieces. So if we have a checkerboard that is n squares long, then we have a few different options. The first thing we could do is place a 1 by 2 piece vertically in the far right. And then we have a 2 by n minus 1 checkerboard remaining. And so if we assume that the number of ways this entire checkerboard could be tiled is an, then once we place this one piece here, we now have a to the n minus 1 ways we can do it because we placed one piece. Okay, now the other thing we could do is to place a 1 by 2 piece horizontally and then another one underneath it, so kind of trapped there. Okay, well then what's left is a 2 by n minus 2 checkerboard, which can be tiled a to the n minus 2 ways. And then the third thing we could do is we could use our 2 by 2 tile here. And again, we get a 2 by n minus 2 checkerboard remaining, which can be tiled a n minus 2 ways. So if we combine this, then we get that a to the n, which is the number of ways we can tile our checkerboard, can be expressed as a combination of the three kind of first move options. And so this is a to the n minus 1 plus 2 a n minus 2 for n greater than or equal to 2. Okay, and so what we need our initial conditions then for a equals 0 or 1. So for a 2 by 0 checkerboard, that can be tiled one way, which is no tiles. So a0 is 1. And then a 2 by 1 checkerboard, which would just be looking like this, can be tiled exactly one way by putting the 1 by 2 piece right on it. So a1 is also equal to 1. Okay, so this is our little formula here. Now we want to go ahead and find the roots characteristic equation. So if we let an equal r squared and an minus 1 equal r and a to the n minus 2 equal 1. If we put that into the expression we have here in red, right, we'll get r squared is equal to r minus 2. I apologize, r plus 2. So we get r squared is equal to r plus 2. So we can subtract r plus 2 from both sides. So we'll get r squared minus r minus 2 is equal to 0. We can factor this, so it's going to be equal to r minus 2, r plus 1, So either r is equal to 2 or -1. So now that we have the roots characteristic sorted out, we want to solve the recurrence relation. So remember we had that an is equal to an minus 1 plus 2an minus 2 but a solution to the recurrence relation is going to be of the form an is equal to a1 r1 to the power of n plus a2 rn r2 to the power of n. So this is going to be equal to a1 times 2 to the n plus a2 times -1 to the n. Okay, so what we know from our initial conditions is that 1 is equal to a0. Okay, so if we put 0 in here, then that must be equal to a1 plus a2. We also know that 1 is equal to a1. So if we put a 1 in here, then we get 2a1 minus a2. So if we add these together, we'll get 2 on this side, I'll sort of ignore this middle piece, is equal to 3 times a1, which implies that a1 is equal to 2/3. And then we can go back to one of these formulas, say 1 is equal to a1 plus a2, put in the value for a1. So 1 is equal to 2/3 plus a2, which means that a2 is equal to 1/3. So now that we know those values, we can put it in to the equation, right? So what we're looking at is, in particular, this equation. Since it's the last thing, I'll just try to fit it up here. So then we get that an is equal to 2/3 times 2 to the power of n plus 1/3 times -1 to the power of n. Okay, and so that is the solution to our recurrence relation.